Hi, this is Mrs. Kidman, and in this video, we are going to be discussing inscribed angles and polygons that are inscribed in circles. So what does it mean for something to be inscribed within a circle? Well, something to be inscribed in a circle means that it is completely put inside of that circle. So an inscribed polygon means the whole polygon is inside the circle. Same with our angle. So let's take a look starting with inscribed angles here. So an inscribed angle is an angle whose vertex is on the circle and whose sides contain chords of the circle. So what that means is we have this image of it on the screen here. We have this initial point that is on the circle here on our side, on our angle, that vertex point, and then it goes through two other points on that circle. Sometimes inscribed angles are also defined as two secant lines that intersect on the edge of the circle, but that is what we're looking at here. So our inscribed angle is that angle that's created between those two rays. And then what that creates is actually something called an intercepted arc. And the intercepted arc is that arc between the two rays on our angle here. So in this case, it's going to be this arc right here. And so what we're going to do in this video is we're going to explore some of the relationships between the inscribed angles and some of the arcs and see how they're related to one another. So let's take a look at this first example here. The measure of an inscribed angle. Well, in this, before we get to our first example, this is a specific property that we care about that's so important. When it comes to an inscribed angle, remember, if it's a central angle, which is the angle created from the center of the circle to the outside of the arc, then our central angle is the same as the measure of the arc. However, when we have an inscribed angle, what's going to happen is our measurement of that inscribed angle, so in this example here, it's angle ADB, the measure of this inscribed angle is actually half of the measure of the intersecting arc there. And so in this case, we've got that half relationship. So say, for example, AD was 70, then that means that ADB, that angle, is going to be 35 degrees. So it's going to be half of whatever that is. Similarly, going the other way, we know that if our angle is 35 degrees, then the measure of our arc is going to be the opposite. So in this case, the measure of arc AB is equal to 2 times the measure of our angle ADB. Okay, so they have that relationship there, that inverse relationship. So let's take a look at a couple of examples where we apply this idea of how we can calculate that measure of an inscribed angle or the measure of the intersected arc. So let's start by finding the measure of angle T. So angle T is referring to this angle here. And so to find the measure of that angle, remember, it's going to be half of the measure of our arc. So if the measure of our arc is 48 degrees, then we're just going to divide that by 2, and we find out that the measure of angle T is 24 degrees. Okay, that one, pretty simple, pretty straightforward. What about the measure of arc QR? Okay, so we're trying to figure out the measure of this arc here. Now, how in the world could we figure that out? Well, what I want you to notice is right here, TR, I'm going to draw a dotted line across it. That is the radius of our circle. And so we learned when we were learning about lines and segments and arc measures that from that diameter of our circle, the arc from one point of the diameter to the other measures to be 180 degrees because it's exactly half of our circle. So that means that from T to R is 180. And so if we can just figure out what T to Q is, then we can subtract that from 180 and get QR. So how can we figure that out? Well, that's going to be that inverse relationship going from inscribed angle to the other side. So we're going to take our inscribed angle and we're actually going to multiply it by 2 to get the measure of our arc here. Now we're looking at the measure of arc QT, not QR. And so we know that this measure of this arc is actually going to be 100 degrees. So from Q to T is 100 degrees. Then what we want to figure out is what Q to R is. Well, we know Q to T plus Q to R is going to be 180. We know the measure of those two arcs will be. And so if this one is 100, we've got 100 plus that measure of QR is equal to 180. Therefore, that means that the measure of QR is going to be 80 degrees. Okay, so this ends up equaling 80 because we can use that relationship knowing that that's half of our circle. Okay, so let's take a look at another theorem here. This theorem says that if we have two inscribed angles in a circle and they both have the same intersecting arc, then the two angles are congruent to one another. So notice how these both have the same intersecting arc of AB here. So it's still the same arc here, this AB arc. And so because they both have that same arc, we know that the relationship between the arc and the interior angle is going to be a 1-to-2 ratio, right? Or yeah, that sort of ratio there where we say the angle is half of the arc or the arc is double of the angle, whatever it is. So if they both have the same arc, then both of our angles have to be the same. It makes sense. So let's take a look at a couple examples where we apply this theorem here. So we want to figure out what RS is. We want to figure out the measure of arc RS. So we're looking for this piece here, and we want to find the measure of STR. So we're going to look for the measure of this angle here. What do you notice about STR versus RUS? Well, based on that previous theorem that we talked about, the arc SR, or the arc RS, is actually the same inscribed arc in angle STR as it is in angle RUS. So because it's the same inscribed angle, that means that the relationship between that angle and that arc is going to be the same. So if our angle is 31, we multiply it by 2, and we figure out that SR, or that measure of arc SR, is going to be 62 degrees, or RS. So if that's 62 degrees, because that's the same intercepted arc, that means that STR is also going to be 31 degrees. They're the same. And we also can confirm that using this inscribed angles of a circle theorem. Let's take a look at one more example here. We were told that the measure of angle E is 75 degrees. We want to figure out what the measure of angle F is. Well, the measure of angle E has the intersected arc of GH. Similarly, if we're looking at the intersected arc of FG, I'm going to highlight that of GFH, or of angle F. I highlighted that in green there. You can see that it has the same intersected arc. And so because they have the same intercepted arc, that means that our two angle measurements are going to be exactly the same, making the measure of angle F 75 degrees. Cool, right? Okay, so do we feel like we need more examples on this? Well, we can always look. Remember, the relationship there to find the arc of the angle, the relationship between the arc and the angle when it comes to an inscribed angle and its arc is the angle is going to be equal to half the arc, or the arc is equal to 2 times the angle. So what we want to do is we can easily figure these out using that relationship. So if we're given the arc and we want to find the angle is going to be half the arc. So in this case, our angle here is 45 degrees. In this case, it's going to be double to find the arc. And so we're going to multiply 38 by 2, and that's going to give us a 76 degree arc. And then the last thing that we talked about is that theorem that says if I have 2 inscribed angles that have the same intercepted arc, then the angles are congruent to each other. So to find this last angle here, we know it's going to be 72 degrees because both of them have an intercepted arc of WZ. Okay, let's talk about 2 more theorems here that we can use. And in this case, we're actually not inscribing just angles, but we're going to inscribe some polygons here. And using the idea of inscribed angles and their relationships, we can actually expand that out to these inscribed polygons. Now in this video, we're only going to talk about 2. We're going to talk about inscribed right triangles, and we are also going to talk about quadrilaterals. If they're not quadrilaterals or inscribed right triangles, there are properties about them, but we're not going to discuss them in this video. So this first one is the inscribed right triangle theorem, and it says the measure of angle ABC, where ABC is an inscribed angle, is 90 degrees if and only if AC is the diameter of the circle. Well, that seems to make sense here, right? If our AC is the whole distance of the circle here, right, then this angle would have to be 90. The reason why is because think about the angle that's created here. So if we have ABC, the intersected arc that's created, if that's the diameter, makes this 180 degrees because we know the diameter from the diameter around the circle to the other point of the diameter has an arc measure of 180 degrees. So because it's an inscribed angle, that angle is going to be half of that 180 degrees, which forces it to be 90. But that is only going to be the case if AC is actually the diameter. If it's not the diameter, then it's going to be something different there. The other property about inscribing polygons that we're going to talk about is the inscribed quadrilateral theorem, which says that if I have a quadrilateral that all 4 points of the quadrilateral that lie on circle C, then if they all lie on circle C, what that means is that the measure of D, so this angle, plus its opposite angle F, is going to be the same thing as E plus G, and both of those expressions are going to be equal to 180 degrees. Now think about why that would be the case. The opposite angles here are going to add up to 180. Well, why do we think that is? If we think of all 4 of those angles, all 4 of them have to add up to 360. We know that's a property of quadrilaterals. And so if all 4 are going to add up to 360, then 2 of them could add up to 180. But because of that specific relationship there, we know they're going to. And so you are more than welcome to prove this if you would like. We are not going to go over that in this video, but we're going to apply this theorem and how it's related. So let's take a look at this first example here. We want to find the value of each variable below. So what did we learn before? Well, we learned that if AB is the diameter, which it looks like it is because it goes through the center, then our inscribed angle is going to be equal to 90 degrees. So 2x is equal to 90 degrees, meaning that x is equal to 45 degrees in this case. What about with this next one? We talked about when it came to our previous theorem here, the inscribed quadrilateral theorem, that the opposite angles will add up to 180 with that quadrilateral. So what that means is we know that y plus 120 is equal to 180, and we know that z plus 80 is equal to 180. So what this does is it forces y to be 60 degrees, and it means that z is going to be 100 degrees. Okay, so we can just use those theorems exactly as they are. Let's take a look at a couple last examples where we apply this here before we get going. Now, the ones on the left are a little bit more simple. The ones on the right are a little bit more complex. So what we want to do is figure out what are each of the values of the variables that we see in these inscribed polygons. So this first one creates a triangle, and we know that it's a right triangle because our inscribed angle goes to this third side, which is the diameter. So that means that x has to be 90 degrees in this case, based on that inscribed right triangle theorem. So if x is 90, or angle L is 90, and angle M is 40 degrees, what does that make angle K? Well, if we do 90 plus 40, we get 130 degrees, and there's 180 degrees total in a triangle. So 130 minus 180 is going to be 50 degrees. Beautiful. Okay, let's take a look at number 5 now. Now this one is a little bit more complex because it doesn't just have a consistent number. We have a couple variables thrown in there. So we know that angle G is 55 degrees. I know that 55 plus y plus 2x is going to be 180, right? Because the interior angles of a triangle sum to 180. We also know that y is going to be equal to 90 degrees. And the reason why we know that is because EG is our diameter, and we were told any right triangle that's created out of the diameter and an inscribed angle, that inscribed angle is going to be 90 degrees. So if y is 90 degrees, and we know that 55 plus y plus 2x equals 180, we can just do that math there where we have 55 plus 90 plus 2x equals 180. And we can go ahead and do that calculation there in our calculator. So if we do 180 minus 90, which is 90, minus 55, which is 35. And so we end up getting that 2x is equal to 35. We can solve for x by getting 17.5 degrees there. Fantastic. Okay, so that was our right triangles. Now let's take a look at a couple more quadrilateral examples. Again, we know that the opposites will add up to 180. So that means x plus 82 equals 180. And we know that y plus 68 equals 180. And so if x plus 82 equals 180, then we know that x is going to be 98 degrees. And if y plus 68 equals 180, then we know that y is going to be 112 degrees. Okay, so that one, again, was the simpler one. Now let's take a look at this other one. What I want you to notice here is how we only have variables in this case. And that's because we know that the opposite angles add up to 180, so we can solve for our variables that way. So let's take a look at this one. We know that s plus u is going to be 180. So what we can do is we can take c plus 2c minus 6 and know that that'll equal 180. So we end up getting 3c minus 6 equals 180. Which means that 3c is going to be 180 minus 6, or 174. And if we take 174 and divide it by 3, we end up getting that c is equal to 58 degrees. So what that means is that this angle is 58 degrees, and our angle U is going to be 58 times 2 minus 6, or 110 degrees. And then we can solve for x by doing 8x plus 10x is equal to 180, and 8x plus 10x is 18x. If that's equal to 180, then we know that x is equal to 10, which makes this angle 80 and this angle 100. And I feel like there was a calculation done wrong there. 58 times 2 minus 6. Wait a second. Do you see where I'm getting stuck? 100 plus 80 plus 110 plus 58 is only 348. So somewhere in here we are missing 12 degrees. Where are those 12 degrees going? Oh, we subtracted this. This should be an 86. Oof, sorry about that mistake there. I'm glad that we caught that. We want 186 divided by 3, which is 62 degrees. So C is not 58. C is 62. Now, what I want you guys to realize here, what I just did is I just checked my work. And an easy way to check your work when it comes to quadrilaterals and triangles is to make sure when we're doing this relationship with our quadrilaterals that they all add up to 360 degrees. So in this case, I accidentally subtracted 6 instead of added 6. So we should have added 6 to this. So C is actually 62 degrees, not 58 degrees. So if C is 62 degrees, then angle U is going to be 62 times 2, which is 124, minus 6, which is 118. And if we do 100 plus 100 plus 80, which is 180, plus 62 plus 118, that gives us 360. So X is 10, C is 62 degrees. So that is how we can use inscribed angles and inscribed polygons and some theorems that are related to them to figure out different portions when it comes to a circle and those things inscribed. If you have any questions, feel free to reach out, but that is inscribed angles and polygons in circles.